Hi, everybody. Thanks for coming. I'm Dan von Cohorn. I do machine learning research in the field of finance. And welcome to New England AI. This is our second year. We started in 2011 as a study group for the online courses from Stanford in machine learning and artificial intelligence. And we could have wrapped things up and closed it down at the end of the class. But the interest in this group has expanded, and it's become this, which is truly amazing and surprising. We have some quick housekeeping, and then we'll get to our speaker. Our schedule is we'll have a speaker first, and then we'll have some pizza and have some time to get together into smaller groups and talk about topics in AI or whatever else you like. I want to remind everybody about the soul of this group. We started as a study group, and that's who we are and what we do here. This place is for teamwork, and you should be using this time to talk about the problems that you're encountering in your research, help each other. Sometimes just a little clue into a new method or system, a new can help save a year of research. A long path that could have led nowhere. So please be open and talk about your own experience, share your ideas. It can help all of us very much. The organizers of this group are putting together a November event that is a week-long event, so that will replace our normal November meeting. If you'd like to get involved in helping to organize that event, it's all hands on deck. We could use anybody who's interested in helping. There's going to be potentially, we're thinking about having some events for kids. We're having other events that are more academic and some that are for early stage companies. So there's a wide variety, and there's something for everyone if you want to get involved. We are here because of the generous support from our sponsors, Beta Fund, HackerDuce, and Google. And so in particular, we should thank HackerDuce for putting us up in this space. They have made it especially nice because we don't have to leave so early as we do when we're over in the Google space. So we can stay past 7, sometimes even some of us past 8. All right, so Brian Ruttenberg is here to talk about probabilistic programming and the democratization of AI. Thank you.
Introduction. Okay. Okay, so as you probably heard, my name is Brian Ruttenberg. I'm here to talk about probabilistic programming and what we call the democratization of artificial intelligence. I'm with a company called Charles River Analytics. We're a small little company out near Arbor Cemetery. So I just want to talk about the goals of this talk. Wait, this is awkward. So the first thing I want to do is I'm going to introduce some basic concepts in probabilistic modeling and artificial intelligence. And then I'm going to detail how probabilistic programs can help people construct and use these probabilistic models. I also want to demonstrate some probabilistic programming concepts and show how some examples using Figaro, which is our open source probabilistic programming language. And of course, I want to get people excited about probabilistic programming. And I know there's people here with varying degrees of skills and experiences, so I've tried to keep it pretty basic. We'll go through a little bit of code, but hopefully not too much. So I apologize if it's too slow, and I apologize if it's also too advanced. But got to try and find that spot in the middle. So let's start with some basics. What do I mean by probabilistic model? What am I talking about when I say that? So let's say I pick a person here at random. And there's some chance that this person is a student. We can model it as either true or they're false. And what we do is we can represent that belief that this person is a student as a variable called student that can take on 2 states, true or false. This person may also be a programmer. Again, it's true or false, and we can just create another variable that can take on 2 states of true or false. Finally, this person may also be eating pizza. We don't have the pizza yet, but let's imagine we are. Again, represented as a single variable with true or false. So now if somebody comes up to me and says, is this person a student? And all I do is see them eating pizza, what do I tell them? How can I essentially reason that this person is either a student or I guess it's a student. So what we do is we build a probabilistic model. And this is a graph that models students, programmers, and pizza eaters in this kind of little world that I've constructed. So how do we do that? Let's start with pizza. So we have this variable called pizza, and we know what makes somebody eat pizza. Well, if they probably eat pizza. If they're a programmer, they probably eat pizza as well. So we can represent this by a directed arrow from the variables programmer and student to pizza that says that the state of pizza depends on the state of programmer and student. But we should back up a little bit, right? This is an AI meetup, so the chances are that if someone's a student, they're probably a programmer as well. So there's actually dependency between the state of the student and programmer as well. So this is we have a little probabilistic graphical model right here. So this is a very, very basic model, of course. It has three nodes. The variables are, the nodes are the variables in the model. And the edges represent influence or dependency between the variables. So there's actually many advantages to representing the world that you're trying to deal with, the world being your scenario or your situation like this. And one of the main reasons is we can mathematically represent these dependencies between the variables using conditional probability tables. So I hope people have a little bit of background on probability theory. We won't go too heavy into it, but we can start building these dependencies into our tables. You can say the state of student depends on nothing. So say student is an independent variable in this world we have, and there's a 0.4 probability that this person's a student and 0.6 probability otherwise. Well, the state of programmer depends upon being a student. So we actually have to make a conditional probability table that looks at the value of the student and determines whether it's a programmer or not. So if they're not a student, they're a programmer with 0.3, and if they are a student, they're a programmer with 0.8. And then, as I said, eating pizza depends on both, so we make another conditional probability table where we represent both the state of programmer and student, and that affects the probability that they're eating pizza or not. For example, if they're neither, then there's only a small chance they're eating pizza. And then using Bayes' rule, we can compute the probability of any state in this network or any variable, and this is what's known as a Bayesian network that probably a lot of you are familiar with or at least have heard. And this is a very, very basic one. So if somebody says, someone's eating pizza, you want to know what the probability that they're a student. So we can infer or reason about this probability of this variable student, given that we have some observation in our model, which is that they're eating pizza. And we can compute this probability using the mathematics of conditional probability distributions, but it really comes out to we want to know the probability that they're a student, given that we've seen them eating pizza. So to answer this question, in theory, it's quite simple to answer, since this is a simple model. Well, first of all, we know this example is trivial. You could also compute the answer analytically, get an exact answer, but for the moment, let's assume that we're not going to do that. We're going to encode the probabilities of each state in some programming language, and then we're going to randomly generate states of this model by running the program in a loop. And then we can record the number of times student and pizza are true in this little model that we've made, and divide by the total number of states we generated, and that's our probability. And it seems pretty simple, but, well, in Scala, so let me just back up a second. So a lot of my coding examples will be in Scala because that's what our probabilistic language, Figaro, is coded in. So I don't know how many people are familiar with it, probably not many since it hasn't caught on much, but Scala is a derivative of Java. So a lot of the programming language constructs that you see will be familiar to most people who know how to program. And I won't get into the nitty-gritty details of Scala unless there's something I need to point out. The point is, you just make our little recursive function where you encode the probability, you encode these conditional probability tables. You say, if some random value is less than 4, then student's true. Now here's your programmer. It depends on student, and here's your probabilities. And then you have pizza, et cetera, the same thing. And you can run this model and get an answer. So this code is actually not too bad. It's quite small, and it's quite easy to do. But the bigger question is, well, what if I had more variables? What if I have 10 or 100 or 1,000 variables? What if I wanted to ask a different question? What if I wanted to know the probability of a programmer instead? What if the pizza is false and not true like I encoded? And what if each variable had 100 different states? Right now we're just encoding variables with 2 states, Boolean, yet true or false. They could take on 100 states. And what if each variable is continuous, like a normal distribution? We're just dealing with discrete data at this point. So the key point is everything about this model, everything about this situation, it's hard-coded into the model implementation that I just made. Nothing can change, or else I have to go back and redo my code. And that's not something we like. So just to give this into our model and think of how, let's say the big Harvard-Yale game is happening this weekend, right? So we get a big influx of students into the town, so maybe that affects the number of students and pizza eaters that just happen to be in town or come to this meeting. So you have this original model here. We add a new variable here called big game, whether there's a big game in town or not, that affects students and pizza. Well, the thing is, these are not actually the same models, even though they look very close. Right? I have to recode everything that I just wrote in Scala, and there's a lot of wasted effort between building these models. So, I coded the algorithm as one step, so I don't get to reuse that algorithm unless I go back and change it. And then, I added just a single variable to the model and could precipitate reworking a significant amount of code, which is something that's not desirable, as anyone who's ever coded up a large model or even a moderate model knows. So we get to kind of one of the major problems in probabilistic modeling is that developing a new model is a really big task, and it's a lot of work. So it requires implementing representation, reasoning, and learning algorithms for everything you want to model. And this becomes extremely difficult as the size and complexity of your model increases. So there's a solution that many people talk about is, what if you could code up these probabilistic relationships in a real simple and intuitive manner that you didn't actually have to get into the nitty-gritty details of how your model's implemented, how your algorithms run, that sort of thing. So you could take your Scala code where it looks like this and just make a couple-line program that includes representing your model, observing the world on your model, and running inference on your model in a couple of lines. And this is a very, very small programming language. Okay, so I just kind of want to go into some background on probabilistic programming languages, just so people can kind of get what I'm talking about and before we start heading into some examples. So, what does it really mean for a probabilistic programming language to enable probabilistic programming? So one of the key features is that you can represent models using the full power of programming languages. That means data structures, control flow, abstraction, rich typing, recursion, all the fun things that you get to do in a normal programming language. You can do the same, except you're working on a probabilistic model instead. The other big one is you want to facilitate model reuse. So if you code up a small little model here, if you can encapsulate it in some sort of reusable atomic unit, you can add a new variable to this model without completely reworking everything you did inside. So you want a lot of code reuse without having to do extra work. Another big one is you want to provide a suite of built-in inference and learning algorithms that can automatically be applied to new models without any extra work. So if you have some reasoning module here that you run on your small programmer student pizza model, you add a new variable to your model, you don't want to have to rewrite this reasoning model. There's no reason why you can't use the same, as long as they have the capacity to deal with that. And finally, we just kind of want to provide a language which imagine new models and new representations. So this is generally a very new field. So it's a new field, and we haven't really fully explored what you can do with it yet because haven't really combined programming languages and probabilistic models that much. So we're coming up with new ideas, new ways of representing models and programming languages, and it's really just kind of a fun way to think about things. So why do we even need these probabilistic programming languages? Well, I told you that building a model is a big and complex task, but why do we even need to build a model in the first place? So let's just back up and look at some of that motivation. So probabilistic models, they actually have a lot of strengths. So they're succinct, so you can represent the relationship between random variables in a simple manner via conditional probability distributions. They're powerful. They can actually scale up to thousands of variables. They're learnable. It's actually pretty easy to construct one given some data that you have. And of course, they're solvable. Many effective algorithms exist to reason on these models, and they actually work fairly well, even for large models. So they can be very rich and model a wide variety of situations. There are models that are hierarchical in nature, recursive in nature, spatiotemporal, relational, infinite. There's a lot of different types of models that people come up, and they're constantly coming up with new ones in the research community. And we want to take advantage of these. We don't want to throw them on the floor because they're too hard to encode. So there's some popular models that people may or may not have heard of. Bayesian networks, one that you just saw. Markov networks or Markov random fields people may have heard of, Kalman filters, probabilistic relational models, hidden Markov models, influence diagrams. These are all flavors of the probabilistic modeling, and each of them have their own strengths and weaknesses. But basically, these form a basis for a lot of everyday tasks that people don't realize is spam filters, speech recognition, computer vision, medical diagnosis, decision making. A lot of this stuff is actually implemented as probabilistic models. So gets out of control. So this is a model I pulled from a group that's trying to do merge semantic ontology. Dependencies, and it gets out of control. And the main point here is that the easy we talk about democratizing model building using probabilistic programming because one should not need extensive training in machine learning or artificial intelligence to build and code a model. And even if you don't have training, it's a real pain to actually build one. And just because I know what I'm doing doesn't mean I want to spend weeks building up a giant model. Time saved. Kind of broadly satisfy two main. Has to be usable, so that means it's intuitive to use. We have some patterns that can be easily expressed over and over again. It can integrate into other applications. You want to use it for real data, for example. It's also an extensible language and has extensible reason. And then we want power. These are not very useful if you can't get the full power of the regular probabilistic model. That means the ability to represent a wide variety of models and the data that's out there. And practical and powerful inference languages that can be reused constantly without change. So these are kind of like the goals that we're looking for when building and working with probabilistic programming. So the basic idea, of the probabilistic program. So when you're building a model in the probabilistic programming language, you're really building what we call probabilistic program. So the basic idea is you have this kind of world, which is a world which is a state of your scenario or situation. And this could be any data structure, a set of real values, arrays, a complete graph, even. In our case, it was just Boolean variables, right, true or false. And then a program, in a sense, is a model of how a world is created in your model. So if you were to randomly generate a state of your model, the program would describe it. So in this small example, this is a program that describes how to generate a world where programmers can do this model. So in our case, the world has a set of Boolean values. This is just some bigger code to actually generate a new state of your model. So that's really kind of this flavor of what we're doing with your executing probabilistic program. But the main takeaway from this is that you don't really execute a probabilistic program once. You actually want to analyze its behavior over the long term. And that means, you want to know things like compute the probability of a single world, given you observe some observations, or compute a distribution over all possible worlds generated in the program, given some other values. So it's really you're executing this many, many times and looking at behavior in the long term, where you get probability statistics and all sorts of other things that you want to find out in the model. So this common process then of probabilistic programming, I broken it down to a 3-step process, and one could argue that it's right or wrong, but in general you code up your model in your language. You apply evidence or knowledge about the state of your scenario in the model. So pizza, that's kind of applied evidence. And then you want to query your model, which is reasoning your inference, or what's the probability that someone's a student. So these 3 basic steps are kind of what we'll go through in the next couple sections. But first, real quick, probabilistic programming background, just to show that this still is an active research field. So this idea of the program as a model, it hints about some of the theory behind probabilistic programming languages. And it's really a research field of intersection of programming languages, AI, statistical relational learning, and actually a lot of cognitive science. So these fields all come together and research unifying this theory of programming languages for probability theory. So there's work on computability of probabilistic programming. What can or can you not compute in a probabilistic program? There's this idea of probabilistic monads, which merges the field of functional programming with probabilistic models. And now there's some work on program analysis, doing symbolic execution of a probabilistic program, seeing behavior, not having to sample them. And there's many different probabilistic programming languages. Each of them have their different research focuses, and they've kind of been, their strengths and weaknesses have driven by their, a lot of times, the motivation of why the people, the team created it. And there's a couple different programming semantics, some can be declarative, imperative, different strengths and weaknesses. So, just a couple other ones besides the one we're going to talk about. Church, which is actually developed at MIT, kind of in the cognitive model routines. That's a functional language based on C. There's BLOG, which is developed at UC Berkeley, model open universe situation. Open universe models are scenarios where you don't know how many objects or things that are in the world, so that's a really difficult. Infer.net, so Microsoft actually has probabilistic extensions to .NET. IWAL, which was developed at Harvard, mainly to do probabilistic relational models. That's a functional language, and there's a couple other ones, Prolog, Factory, and some more, and I apologize if I didn't mention your favorite one. And of course, there's also Figaro, which is generally what I work with. So that's what we call an object functional probabilistic programming language. It was developed by Avi Pfeffer when he was at Harvard. He also did IWAL before. This is his newer one. He did at Harvard, now he's continuing the research at Charles River Analytics. We call this object functional because it combines functional programming and object-oriented programming, which in general means Scala. So our programming is in Scala. The functional programming provides a lot of powerful representations and a lot of great reasoning building blocks. And the object-orientedness provides essentially what a lot of object-oriented languages provide is easy representation of common design and extensibility. So we're kind of getting that for free just by using Scala. We'll go through the three basic steps of probabilistic programming in Figaro. How do you build a model? How does the model get applied? And how can one perform reasoning on that model? So we're going to go through a little bit of code. I hope it's not too much for people. And yeah, you can always ask me later if there are questions about the code. So building a model. So it's a library in Scala. So basically you import essentially a bunch of packages like in a Java import. So this is essentially the guts of the model, but we want to kind of go in and see what we're actually doing underneath that. So the core of Figaro is called this element T class. It's parameterized by this kind of T. And elements are just Scala classes that represent a random or non-random process that produces a value. Simple enough. So for example, we said val student. So in Scala, val is just an immutable variable. So it's the same. For our purposes, it's the same thing as a variable. So val student equals flip 24, which just creates an instance of an element class that we call flip with the parameter 24. And flip just represents a random process that produces a Boolean value true with 24 probability. It's just a Bernoulli value. And then I found when generating values from this random process that the student class represents, I can just call student.generate, which will set student.value true with 24 probability and false on that. So it means to generate a random value from this process that you just did. All random processes in Figaro are represented by elements. But keep in mind, these are still Scala objects in the Scala language, so we can actually manipulate these random processes in Figaro like we do for any data structure. We can stick them into maps or sets, or we can do whatever fun things people do with data structures in a normal programming language. But now these are actually random processes. Another key point is that elements are parameterized by the type of values they produce. So when I said element flip, which produces true or false, that's an element of type Boolean. And this parameterization is really one of the very key strengths of Figaro and for probabilistic programming in general, is you can create elements or essentially random processes over anything. It could be basic types like integers or doubles, classes, entire processes. You can create a random process over a suite of functions. In some of the examples that we showed in Figaro, there's a couple examples of building a random process over DNA sequences or graphs. So any parameterization you can do in a random Figaro model as well. And then building your model essentially consists of creating Figaro instances and then piecing them together how you want. Sounds simple, and generally pretty easy. So it has a couple, it has a library with a bunch of elements from common processes. Easy one, like constant, just returning the same value with probability 1. Flip, which is solve, just prove the trial. Select, which is a categorical distribution, says select a value at random from a list according to some given probabilities. And then there's a whole gamut of a lot of continuous and discrete probability distributions that people use in most probabilistic modeling, uniform, normals, etc. There's much more than that. We don't need to look at those. It's not that long. So recall that this small model actually contains conditional probabilities. So pizza depends on the student, etc. But the element that we just made, called flipped, 0.4, is not a conditional random process. The probability of true is fixed when the object is created and stays that way forever. So we actually need a method to make conditional probability distributions, and we do that with what are called compound elements. These are elements whose parameters are conditioned on the value of other elements. I would make a conditional probability distribution, which is exactly the sort of thing we want. So for example, I can make a compound normal distribution. So I'm going to create first an element that's a uniform, discrete uniform probability distribution that's going to take on values of 1, 2, 4, etc. to 10. And then I'm going to create a normal distribution where instead of giving it let's say a double value of the exact mean, I'm going to give it the element that I just made. And what that's going to do is it represents a normal distribution whose mean is uniformly selected from 0 to 10. So you can think about it as this uniform distribution creates 11 different normal distributions, and at any one time we're only looking at one of them, whichever the uniform value happens to be. And just for some terminology, we usually refer to the elements that another element depends upon as the parents of the element. So this element mean is the parent of this element norm, since it's used in the arguments. So looking again at our pizza model, it actually contains 2 compound elements. So the first one is our, well, this is a non-compound element, which is split, right? It's the non-dependent element. Then we have 2 elements. If, which is right here, that says select between 2 elements depending on the value of the Boolean element, of the Boolean parent element. And note this is not the Scala if reserved word, as in a normal program. If is actually a Figaro class, where you give it an element and then 2 other elements as the case conditions. And then CPD, which is short for conditional probability distribution, basically selects an element based on the values of the parent elements. And this is just an explicit way to conduct a conditional probability table. But these are compound, right? Because depending upon the values of the program and the student, you would select one of these elements right there. Then I'll just talk about 2 kind of really key elements in Figaro that kind of give a lot of language its power. One is called chain, which maps computation from the space of an element T to the space of an element U. So it's taking an element of one type and converting an element to another type. And then apply, which lifts a function from the space of values to the space of elements. And I'll show some more details in a second, but if people are familiar with functional programming, these are called probabilistic versions of the monad. So chain is the bind and apply is the end. So chain represents computation from an element T to an element U. And its name actually is indicative of what it actually does. It chains together probabilistic computations. It takes 2 arguments. You give it a parent, which says, what is this chain conditioned upon? And it takes a function, a Scala function, from a type T and returns a new element from that value that used to be given. And for example, we can rewrite this compound normal that we just made previously as a chain. So again, we create a uniform distribution from 0 to 10. And now we create a chain that says, depending on the value of the mean, here's the function. So in Scala, you can write anonymous functions just by writing the argument list type, and the right arrow, and then what you want. So this is just an anonymous function. So here's your function, take an integer, and depending on that value of the integer, create a new normal distribution. And sampling then from a chain has some sort of special semantics. What does it actually mean to sample from a chain? Because this does represent a random process, but we want to make sure it represents what we want. So to if you want to sample a random value in the chain, it's really a three-step process. We generate a random value from the parent. So in this case, we generate a random value from this discrete uniform distribution. You would call this function, in this case, it's this random function here, which will, does whatever it does in there and returns an element. In our case, it was a normal distribution. And then you sample from this, again, from this normal distribution as the value of the chain. So all this computation essentially gets reduced down into this chain element, and then you sample from there. And why is this important? Well, actually, many model classes are actually implemented using chains. So this code that I have here is actually almost the exact same code to do a compound normal distribution, but many other elements are actually implemented as chains. So if, that we saw earlier, is the same thing. So if takes in the test element, then clause, and else clause, and it's basically just doing object-oriented extension of the class, extending out the chain. It takes the parent of the test element. It's going to apply this function. If the test element is true, it returns this element. Else it returns that. Pretty basic. But the key point is that chain can actually change the structure of your probabilistic program as you sample, or as you run it, or as you're doing inference. So this is one of the key strengths of probabilistic programming, is that reasoning on your model is not just considering the space of values produced by a model, but really the space of structures produced by your program as well. So ultimately, obviously, you're looking at, let's say, the values of what you're trying to do, but getting those values can explore a wide range of structures that can help infer what you want. Inside the chain, we can create an entire, all new elements. We can create an entire Figaro program inside the chain and return it and add that part into the model as well. So the next kind of special element is apply, and this is basically an element that allows any Scala function to be integrated into Figaro models. So you consider it as you're lifting an arbitrary Scala function into the space of elements. You can then use it in a probabilistic model. So, like chain, it takes two arguments. A parent, again, another function, but instead of returning an element, it just returns that. And what can you do with it? Well, for example, a distribution over the sum of two normal distributions. You want to add two normal distributions together and know what the distribution is. So you create two normals, and you use apply, you give it both normals, here's your anonymous function, just add them two together. Sampling from this apply, you sample from a normal sum distribution. And you can also do fun Scala things like convert tuples of elements and elements of tuples. That's just some Scala semantics right there. But one of the important points is, at least in Figaro, is that Scala is completely interoperable in Java. So any Java class, object, or function can actually be integrated and used in your model. So you can do, open up a socket in Java and bring that into your model and use it to reason with. Anything you want. And we've actually had some fun with that. So putting this all together, let's make a nice example, show you a nice example that exemplifies kind of probabilistic programming. So we're going to combine two of these powerful constructs. One is chain in Figaro, and since Scala is a functional language, we love to do everything via recursion. So we're going to show you how to do that. And a good example of this is PageRank. So I don't know how many people are familiar with PageRank, but it's Google's PageRank. It's a model of a probabilistic process on graphic web pages to determine relevance and essentially when you do a search, which ones you reach. So we'll do a slightly modified process in Figaro for simplicity. So each web page on the internet is a node in a graph, and you draw an edge between web pages when they share a link. Of course, the real PageRank uses direct edges, and the real PageRank is much more complicated at this point, but this will serve illustrative purposes. So the probabilistic process is known as a random walk. The way it works is you start at some node on the web page, your web page graph, let's say this node right here. You randomly move to one of the node's neighbors. In this case, not so random since it only has one neighbor, but the point is you repeat that process for some amount of time. You jump here, you step back, that sort of process. You record all the nodes visited, and then the more times a node is visited, the higher its PageRank. So that's kind of the general concept. You're moving around. And people who probably know, this is not the way it's really done. This would be done via matrix computations, giant matrix computation, but again, this is for illustrative purposes. So what were they probabilistic model look like a kind of model of a random walk? When you have your starting node, and depending upon the starting node, you would have a variable that's called neighbors, the neighbors of that starting node. And depending upon these two values, you would jump to your next node. And your next node would have a set of neighbors. And then using that, you would jump to the next node, et cetera, et cetera. You keep going down for however many steps that you're actually wanting to take in your probabilistic model. Well, this is actually quite tedious code in a non-probabilistic programming language. So first of all, neighbors at each node are different. So you kind of have to encode that in these variables. You have to make one giant case statement that says, if the node you jump to is X, then these are possible nodes you can jump to now. And what if the structure, what if the web page graph structure changes or the number of steps changes? You could go back and redo all of these tables that you did. All this extra work you have to do completely out the door because some small changes in your giant web page graph. Web pages change constantly, so that's a relation. So we'll do this in Figaro, and hopefully it'll be a little simpler. So this is how we'll get to the most code. And, hopefully, people can follow. So we'll start by defining some data structures. It's going to be basic. Class to do an edge, class to do nodes. Pretty simple. And we'll define some parameters of a random walk. So maybe we have some code up here that generates a graph, and maybe it exists already. That's not the issue at the moment. We create a start node, which is, let's say, node 0. Now, this is basically this is a Scala operation. We have to lift it into the space of elements so we can use it in our model. So we can just create a constant using that starting node. And you notice that the type of this start node element is an element over nodes. Now we can use it in our model however we want. And then let's create an element that represents the number of steps to take in a random walk. And we'll just say we'll take uniformly between 1 and 20. We'll select that many steps to take in a random walk. And this is an element over use. So we're going to create a chain that essentially builds the model from different parameters. So there's one chain statement here, which I call random walk. It's an element over a list of nodes. And this is basically going to return, this chain is going to return a random process that defines a list of nodes you've visited so far. So it's going to be subtracting order. You create a chain that takes in your parent values, which are the number of steps you're going to take, and which node you're going to start the walk from. And then each time these values change, you're going to call this function called walk function, which I'll show you in a sec, but it's basically going to generate a new random walk each time you want to randomly regenerate these values. So this is what the walk function looks like. Again, it uses recursion. So it takes in the number of remaining steps to take and the node to start from. It's going to return, again, a list, an element over a list of nodes. So this is the terminating condition. We can kind of skip that. What essentially it does is, the first thing it does is it calls itself repeatedly and subtracts a step. Once it returns, it's going to return an element over a list of nodes. So these are the previous nodes it's already visited. It's going to take a step using this function. It's going to return the next node you're going to visit. And then it's going to concatenate the next node you visited with your previous nodes and return that. And in Scala, the last line of a function is an implied return value. So it's going to return this new element here, which is an element over a list of nodes. So in this step function, this is where we're actually going to do sort of the random walk process, just take a step. It takes in history. These are all the elements you've already visited on the random walk process. And it's going to return the next one you're going to visit. And what we do is we create a chain that depends upon what you visited so far, which is, of course, what we want, because the random walk depends on where you've been before. We're going to grab the last node you visited. L.tel is just the last node in the list in Scala. And we're going to create a categorical distribution that says, take all the edges from the last node that you visited and randomly select one. And I won't get into the Scala semantics here, but essentially that's creating a list of edges and a list of probabilities and sticking that in this column. And that's going to return this chain, which represents, given where you've been so far, where do I want to go to next? And that's it. Those, that one element declaration, those two functions, can instantiate a random walk over however many steps you want, what sort of graph you want as well. And the simplicity really hides the power behind it. So each time this function is called, so that means each time your parents change, you're taking another step or you want to change something about your graph, it creates a new set of elements that model the next step in the random walk, depends only upon the previous step. So we're kind of building in a lot of this expansion and contraction here automatically. In fact, we can look at it sort of visually that says, let's say the number of steps you take are 3, your model looks like that. But if you resample this value, your model automatically expands to add these new nodes in your probabilistic model, and you don't have to do any work because you've built it into this recursive function that's going to expand and contract as necessary. And that's really one of the powerful aspects of Figaro and probabilistic programming in general, is you can sort of create and expand the structure of your model as well. So that's essentially one example of building models in Figaro and probabilistic programming. So the next thing is applying MXL. So once the model is built, we'll actually want to do things with the model, and just usually build models for no reason. So usually this is you observe something about the model, you have a preference to some state of your model, and you want to mention your. So you can do this through conditions or constraints. And the condition is just a function from a value to a boolean. And this basically says it's an observation on some state of the variable. It returns true if the variable is in that state, and false otherwise. So an example in our random walk is this is the number of steps we're going to take in the random walk. We can add a condition that says take the value of the random walk. If it's 10, return true. If it's false otherwise. So we only allow the value of the number of steps. Another way you can do it is it's called a constraint, sometimes known as soft constraints, that takes a value and returns a real number. And this is essentially saying some value of your element is more preferable over other values or elements, given all other things are equal in your model. Again, in the number of steps, if we want to add a constraint, you can just say add a constraint, and you say, well, if the number of steps, the current value is 10, we give that 2.0, else we give 1.0. So we're saying the probability that number of steps is 10 is twice as likely that it's 1. And that's sort of an observation that you want to put in your model, and you may want to reason with that. This is especially useful in undirected models. So undirected models are basically models that don't have directed edges, and they can actually model a lot of different dependencies that directed models can't. So these are also known as Markov networks or Markov networks. One of the canonical examples of this is it's called smokers and friendship. People who smoke tend to have friends that smoke. People who don't smoke also tend to have friends who don't smoke. So you can represent this by an undirected model. Brad smokes, Bob smokes, Alice smokes, and they have an undirected edge. So here's just a quick example of how you can use constraints to build this model. I won't go into this too much detail, but you create a class called person that determines whether they smoke or not. You create 3 people, you have a list of edges. And then for each edge, essentially you're going to do what's called adding a constraint, which is a smoking influence function. This function takes a pair of booleans. So remember, your smoke is a true or false value. It says if they're the same, return 3, else you return 1. So it's 3 times as likely that friends smoke, or 3 times as likely that friends don't smoke. But if they return one of them smokes and one of them doesn't, that's less likely. And then you can do something like add a condition and you say, oh, Alice smokes, and you say that's right. So this is just an example of how you can use conditions and constraints into arbitrary functions to kind of build an undirected model. The last step is reasoning on your model. So, as I said, we just talked about model building. Usually we're going to query for some information. That means we want the distribution of some variable in the model, given some evidence. We want to know some statistics about the model. We want to put it to use. So to answer these, we do what we call inference, or reasoning on your model. And this is actually where many of the benefits of probabilistic programming are realized. Most inference algorithms work out of the box, or any model that usually creates this, especially true in big models. So to use an algorithm in Figaro, it's quite simple. You create the algorithm, so algorithms are also data structures in Figaro. You say, you declare, you give the algorithm a class. In this case, it's important sampling, which is called importance. You give it the parameters, in this case, it's number of iterations, and then you get a list of elements that you're going to want to query when the algorithm is complete. And you query, and you want to know something about this element when you're done. Maybe it's probability, maybe it's some stable distribution. And then you run the algorithm. And figure out that's one line. You say algorithm.start. And your algorithm runs, but underneath the hood it's actually doing a couple different things. There's 2 types of algorithms that actually, there's 2 ways to run an algorithm. So one is called one time, which is run the algorithm once, produce the answer. So in this case, this is a one-time algorithm because it's going going to run for 1,000 samples and then quit and be done in the query. The other idea is what's called run anytime start, which is the algorithm runs continuously in a loop, not in a loop, but just runs continuously until you stop it. And as the user stops it, then they can query it and do what they want with it. If they don't have the answer or they want more computation done, they can then restart where they left off and keep going and repeat that process. So, you have, in this case, it runs for 1,000 samples. You say, well, I don't know how long 1,000 samples is going to take. I know I have 10 minutes. You can just run for 10 minutes and we'll use that answer. And then finally, you want to query the algorithm. So, there's a lot of different types of queries you can do in Figaro, but I'll just pick a couple. So you can say, compute the expected value of an element under some function. So in our random walk model, you can just call algorithm.expectation. Say this is the element I would query, and you can say, give me the expectation under the length of the unique number of nodes of visitors in the model. This is just taking a list and turning it into a data. And then you can query the probability of a specific value of an element. So again, you can say algorithm.probability. Here's the element. You say, what's the probability of this element taking on this exact value? You give it a list. This is a data structure. You're saying, I want to know the probability that's going to contain a list of nodes 0, 1, 2, 3 in that order. So that's something that you can actually query. And then we talked about constraints and conditions before. So you call the smoker's example, you create your algorithm, you apply your constraints and your conditions. There's actually no special handling needed when you run an algorithm or a model with constraints and conditions. You implement it the same way. You just call the algorithm, you give it what you want, you start it, you create the algorithm. All the conditions and constraints that you attach to your model are handled automatically underneath the hood as the algorithm. You don't need to change it. So just one thing to note is the common algorithm usage. So we talked about 3 models today, the random walk, the pizza, and the smoker's model. This is how we implement importance sampling on all 3 of them, and then do a query. So instantiate the algorithm, run it, query. It's the exact same for all of them, and that's one of the real key strengths that I want to drive home today, is that running, creating and running and querying an element is the same for any model. I can say that in general that's the case, but sometimes there's exceptions, but there's a wide range of models that you can build that you'll never have to change how you query it or how you run it. And that's very, very helpful. You don't need to worry about how do I implement an algorithm for your model. And just for completeness, this is a complete random walk example we talked about. We don't need to go through it, but the point is that everything the model of the scenario is in this code. That means creating the model, applying observations about the state of your model, and querying model all on this, 20 lines of code, which is a nice improvement. So the Rest of Figaro, there's actually a lot that they talk about. First, since it is an object-oriented language, it's very extensible, and it's designed for people that actually create their own elements and algorithms. Inference algorithms is still a very active research field. There's new algorithms that we create all the time. We don't want to freeze this language. We want it to grow as new research finds. New research finds better ways of doing it. So there's an extensive suite of traits which are just Java interfaces. Abstract classes and types really make that easy. So you can design your own algorithm or your own random model or your own element. If there's a distribution that we don't have, you can create it. It's pretty easy. And then there's more features you can touch upon. You can name elements and do all those things with that. Of course, there's many different inference algorithms, markup chain Monte Carlo methods, filtering, factor-based algorithms. We have decision making in it, and we have some doing some grammar learning in it, and there's other things as well that people can find out. So to wrap up, just a couple of more information points. So Figaro, it's free, it's open source, it's available now at cra.com/Figaro. There's a tutorial release. So version 2.0 release is imminent. And I say this Friday is our target date, and anyone who's done any software design knows that that is not necessarily true. But all the code is done. We're just waiting on the lawyers to give the stamp of approval. But as of this 2.0 release, which has a lot of new features, including decision making and grammar learning, we're going to move all of our development to GitHub. And you can find the website here. It's called GitHub P2T2. Has some obscure name because we're actually doing a lot more than just Figaro. We're doing a lot of some general probabilistic programming tools. And of course, you can always contact me on my email address here, or you can email Figaro@cra.com. And And I was told that I could just go straight to hobby, so that's where we probably answered it. And for general probabilistic programming, if you're interested in just this general field and want to find out more, there's a great webpage called probabilisticprogramming.org. Has a lot of general resources, a lot of different languages, tutorials, background papers. You can pretty much find whatever you need to line up from there. There's probabilistic programming workshops now in the academic community. The last one was at IMS in Tahoe, and I don't know what the next one's going to be. And then there's actually a new Arbor program, probabilistic programming, that's likely to produce a lot of new papers and workshops, a lot of new research that's going to come out of that. A lot of people are pretty excited about that. So just to conclude, probabilistic programming allows people with little AI or machine learning experience to take advantage of the power and utility of probabilistic models. And hopefully I came across that Figaro is a nice probabilistic programming language that's easy to use, it's powerful, and it's flexible. And I really just encourage people to kind of get active in this community and start trying experimenting with any probabilistic programming language. It doesn't have to be Figaro. So, happy ends. So that's pretty much it. Thank you. And any questions? Yes?
Maybe give a quick summary of how Figaro compares to Ver.net and maybe
Not really. So, if Ver.net, definitely, that's in the Microsoft community. I don't really have much experience with that. Church, I don't have much experience with either, to be honest. I've seen a little bit of the semantics in some of the examples. I think, so Church was designed in the cognitive modeling kind of framework, so it was designed to do a lot of work in that sphere. I find Church is pretty powerful, but the programming semantics are not what I'm used to personally in terms of regular programming language. And I don't know, I think Church is all MCMC based, so I can't remember exactly. So that's pretty well I can tell you. There's actually quite a few ways where the Church community is probably going to do information on that. Yeah?
Why do you find that the expressing this as programming language rather than special data structures is superior?
Can you repeat that? I'm sorry.
So it seems like, I've expressed probabilistic graphical models as data structures before, and it seemed to work pretty well. And this is my first experience or introduction to using the basis of language for it. Could you talk about why the difficulties, I guess,
Well, I think one of the key points is that, yeah, you can represent probabilistic models as data structures before, but what we're doing in, say, Figaro is forcing you to use a specific type of data structure that can represent a random process. And given that everything is expressed through this type of data structure that, underneath the hood, there's a ton in there that we can show you, but all the inference algorithms cannot work on these data structures in a common way without knowing the specifics of how you implement it. In terms of, let's say, an object-oriented design, standard elements for encoded probability distributions have certain things that have to satisfy. They have to have a density function. They have to, return a transition probability when you do MCMC methods. So we can force people to use essentially a common data structure where they can just override what they need to do in terms of their random processes, and the inference algorithms automatically know how to handle these data structures. So it's not that, people have done probabilistic modeling and data structures before, but whenever it's out there doing their own, you don't kind of get this common inference algorithm. Yeah.
If you go back to the AJAX example, I'm curious, if I had constraints like I want to visit the node 10 at a fixed step, something like that, how efficient will the sample be?
Poor. Yes. I mean, have intelligence in what algorithm.
I guess the question is, it's not smart enough to figure out, oh, this is the right sound method.
Not yet. Not yet. That's one of the things we're working on. And that's one of the things where we push some of the intelligence back on. Yep. Metropolis savings, variable elimination, Ford sampling, as you saw, Ford sampling. We have an implementation of belief propagation that is nearly done, but not ready to be released yet.
For some of these, structure
yeah, we're not at the point where somebody can just write a model and just say go. We still assume some experience in machine learning, like knowing that your model is continuous and we shouldn't stick it into a variable elimination algorithm. We're kind of making that distinction. So as we talk about this new Java program, that there's going to be a lot of work on how can we even remove that step. Can the user just give it? We'll figure it out what algorithm would be best for it. How particle filtering. And then there's some decision. And some EM and parameter business. Not in general. Yes?
How does the performance compare to other implementations of the same algorithm?
That's a good point. So it won't be as fast. You have to be honest in this case. It's Scala, which is running on the Java VM. And it won't be as fast of an implementation if you do it in C, for example. There's no question about that. But we feel like a lot of the time you save programming your model will be saved on inference as well. And a lot of work has gone into memory management and efficient inference and what they're trying to compute. So there's before and there's good ways to build your model that can result in faster results. So, you'll never beat a native implementation of some of these algorithms. But in a sense, that's not necessarily what we're going for. We're going for usability rather than speed.
So how do you query additional probabilities from model?
How do you query conditional probabilities? Well, the conditional probabilities are built into your model. How you construct it. So maybe I'm not answering your question, but you can tell me if I'm not. Let's go back to our example. It's a nice easy example. Okay, so the conditional probability of pizza given a programming student are built into when you construct the model. So if you that's sort of what the
that's more than a wedge away. So the probability that, say, a student wants to have a load of pizza and then they are studying music.
Okay. Assuming you put music in your model.
Right, assuming that music can have a load of
Yeah, so what you can do is you can actually make an artificial edge from ones. That's essentially an plot that puts them together, which is essentially you're just creating a couple of values in the track. That's a good question. You could always, yeah, that's a tricky one. I've never tried going that far. Yeah, we can do that, but there's nothing explicitly in the query semantics that says, here's two elements, give me a conditional probability of one on the other one. In some, but that was a really, sorry? Yeah. It's one thing to, let me grab that maybe it's important for a while. Yeah.
Do you have anything built into these kind of visualizations? You have a model in there. If you have a model, construct it, like model, it's nice to go back to the graphical representation, but they're giving you things built in, so the model gives you a graphical representation.
No. That's a very difficult thing to do, especially when your model is expanding and contract structurally, given what you code. So we don't have that. We may work on it. I'm not sure. We have other graphical representations of probabilistic models. For example, probabilistic relational models, which are essentially object-oriented Bayesian networks. We do have some ground linear system, so you can see them as well. And those compile down to Figaro, but there's nothing that you can say, here's my code, visualize it for me. But that may be the scope of some of the, say, our program to manage that. Yeah.
I gather you don't have this now. Is there any options there? Well, maybe you do. Can you, I know there are algorithms, you can take them out, you can feed it down, and say, recalibrate the model based on this data.
You would learn it, right? Yeah.
Right, so true edges, new edges, tweaks, probabilities, start with this is your basic model.
So there's two issues you're talking about. You know, there's, let's say, you're trying to learn the data in your model with traditional probabilities, and then what you also mentioned is learning the structure of the model. Yes, so we do have some parameter learning in there now, which uses EM essentially to learn the parameters of the model, give some priors and some observations. Structural learning will be a top task. That's definitely on our radar. Structural learning is a non-probabilistic programming language, just in a regular Bayesian network, is a difficult problem.
Yes.
Structural learning in a probabilistic program, I think that's going to be a significant task for us.
What are the next steps for Figaro? What are you planning to do next?
After Friday. After Friday. The two big ones we have, one is belief propagation. It's a pretty widely used algorithm that we have noticed has been lacking. It's nearly done, we should get that out soon. The other one is, it's kind of been our area for a long time, is making this distributed. So distributing out some of the competition. The computation, make it multi-threaded, have them essentially work on network sockets, that sort of thing. So those are the two big ones. And we had this release on Friday, we were in GitHub, release on Friday, let's say, you can see giant list of tasks that we're going to post as well that maybe some enterprising people in there will take on and do. But there's just a lot in there. And I think another big one, which would be automatic kind of algorithm selection, pulling up at a level above that says maybe we can make the user less algorithm. Yes?
Speaking of algorithm selection, have you thought about how to arrange large complex models where inference algorithms are appropriate parts?
That's a good question. No. But again, that is also within the scope of what's been reported in the release. We actually can do that fairly easy. So there's this notion of a universe in Figaro that says elements that you create live in a universe. And you run an algorithm on a universe. So if you create a model that consists of two universes, say happens to one, happens to the other, you can actually run different inference algorithms on each one and condition one algorithm to the other, and vice versa.
They talk to each other during.
Yes, they can. So their dependencies still exist, right? You create objects that depend on other elements. The other element can live in another universe, just that the inference algorithm runs will restrict itself to elements of that universe. So you have to do some tricks to go back and forth to make sure you're sampling well for both universes. But for example, we do have an implementation of variable elimination that allows you to use continuous models where it will sample your continuous data in some universe, do variable elimination, and kind of go back and forth and do that to kind of get an idea of what your data is conditioned on the continuous data. So in automatic way we do that, we don't have yet, but there is a nitty-gritty way to do it. And that's kind of the general theme. A lot of this is almost everything you can do. It's just how deep into the code you want to actually do it.
Thank you, Brian.
Thank you.
Thank you.